Hello friends, in today's class we are going to talk about methods for handling deadlocks. Welcome here, and we are talking about methods for handling the deadlock. Now we have few methods which will say that which will make ensure that it never enter into the deadlock. Okay, never enter into deadlock. Okay, so that methods will ensure that deadlock will not occur. And the second method is that let the system enter. Let the system enter in the deadlocks, and after that we will recover. Okay, so two strategies, both are different here in this case, and we are talking about ensure that the system will never enter in a deadlock state, and we are having two categories: deadlock prevention and deadlock avoidance. Okay, so we have two methods: deadlock prevention and deadlock avoidance, and that will ensure that it never enter into the deadlock. Second is allow the system to enter the deadlock and then recover. Ignore the problem and pretend that deadlock never occur in the system used by the most operating system, including Unix system. Okay, so we have no strategy for handling the deadlock. Prevention, at least not allowing, let it go into the deadlock and then we will recover. So prevention is restrain the ways the request can be made. Okay, it restrain the ways in which a request can be made. And mutual exclusion, not required for shareable resource, that is read-only files, readers, and must be hold for the non-shareable resource. Hold and wait must guarantee that whenever a process requests resource, it does not hold any other resources. Okay, so that we need to break. Okay, because that is the main cause of the deadlock, that you're holding a resource and looking for another resource. So here this wants that that process request a resource and it does not hold any resources. Require process to request and allocate its resources before it begin execution. So we want that all the resources, all the required resources should be allocated before it begin the execution, or allow the process to request resource only when the process none allocated to it. Yes, that is the problem with this, that we will have a low resource utilization. Okay, and starvation is also possible, that suppose one process is denied for all the resources and the process is waiting for what? Waiting for all resource available. Resources available. Okay. No preemption was one of the reason, and if the process holding some resource and request another resource cannot immediately allocate it, then all the resources of the currently being held are released. Okay, so if you're not able to satisfy the request, then make sure that it also releases all the resources. Preempted resources are added to the list of the resources and the process for which process is waiting, and process can be restarted only it can regain its old resource as well as the new resource. Okay, so what we are that all the four condition mutual exclusion, that we are not denying mutual exclusion for shareable resource. Yes, we required it. Hold and wait will not allowed, that that has to allocate all the resource before it begin its execution. No preemption means that you cannot hold that once it is allocated, it cannot be voluntarily release the resource. That we don't want. We can force them to release the resource, and A circular wait impose the total ordering of the resource type and requires each process request resource in increasing order of the enumeration. Okay, so always P0 to P1, like we will maintain the enumeration order P0 to P1, P1 to P2. We don't want that this will break by Pn is going to allocate the resource in this way. So in this deadlock prevention methods are that the main cause of deadlocks, that four conditions occur simultaneously: mutual exclusion, hold and wait, and no preemption and circular wait. We don't want this condition to hold simultaneously. So if this condition does not hold, then definitely deadlock will be prevented. Okay, deadlock will be prevented. And yes, we have some issues with resource utilization, and but that is the cost we need to bear for deadlock prevention. Deadlock examples, there are many examples are there. Like one of the example we have already seen, that if there is a variables, two resource A and B is there, and here is the deadlock example that I already told you. This one, that if you have a two semaphore A and B and initialize to 1, and that is something happening, that you acquire A and it acquire B, hold it, and then waiting for B, and this is waiting for A, hold and wait, and circular wait is also there. No preemption, we cannot hold any other to release its resource, and then all four conditions are made. Okay, so that is the basic example of this deadlock example. Okay, avoidance. Okay, now the second part here in this case is deadlock avoidance. Requires that system has additional prior information available. Okay, so we need that some additional information available, and that method we are calling it as deadlock avoidance method. The simplest and most useful model is to declare the maximum number of resources of each type that process may need. Okay, so you declare that process P1, suppose there is a R1, R2 and R3, three type of the resource. You say that I need 4 of this, 2 of this, and 1 of this resource needed. Okay, so that prior information that we need for this, and deadlock avoidance algorithm dynamically examines the resource allocation state to ensure that there can never be a circular wait condition. Okay, so that will dynamically examine the resource allocation state. Okay, so that circular wait will not occur. Resource allocation state is defined by the number of available allocated resources, the maximum demands of the process. Okay, so the resource allocation state is defined by the number of available, allocated and maximum. Okay, so that is something like it is talking about here are the requirement of, as I told you, R1 is 4, R2 is 2 and R3 is 1. This is its maximum demand, as I told you. And availability, suppose R1, R2 and R3 is suppose 6, 4 and 5. Okay. And allocated here in this case, I have already allocated 2 of it. R1 allocated, available, and this is max. Okay, available, suppose R1, R2 and R3, and this is 1 and this is available. Allocated is suppose 2. Okay, so now can I make this process requirement? So yes, if you take available minus allocated, that is 4, 3 and 3, and that is sufficient to meet the demand of this particular process. Safe state. Okay, so an allocation will be when I can say, if after all, this is the point that we are talking about. The need vector is there, the available vector is there, and allocated vector is there. Okay, so in this case, when we call it as a safe state, we need some prior information, and in that information, when we call it as a safe state, When the process requests an available resource, system must decide immediate allocation, leaves the system in a safe state. So what is a safe state? A safe state is a sequence of state P1, P2, P3. Some, okay, not necessarily in this order, P1 in some order, okay, of all the processes in the system such that each PI, the resource that PI can still request can be satisfied by the current available resource plus resources held by the Pj where j is less than equal to I. Now it looks, definition wise it looks complicated, but it is really a safe state. Okay, so we have to find a sequence. There exists a sequence of what? Sequence of processes. We need to find a sequence of processes such that we look at what? We look at its available resource and resources available. Like here, if I say that, suppose here I made this demand. Okay, made this demand over here like 423 is the required one, maximum need of it. Okay, so what it will do is it will be allocated, and after this it will release the resource. Okay, I can give you a better example. Can I? Okay, available says, suppose this is a maximum requirement. Okay, look at here, and here okay, let me give you one more example here. What is trying to say in this case is this. So what it is trying to say here, that suppose P1 is holding a resource 1, 1 and 0 for R1, R2, R3. Its maximum requirement is suppose 2, 2 and 3. Available is suppose we have 3, 3 and 3. Okay, this is the availability. The rest has been not allocated here. Okay, so now what will happen? This is my maximum demand. So need is what? 2 minus 1 and 2 minus 1 and 3 minus. This is my need. This is the need of this process 1. Let's say this is required need 113. Okay, so now what will happen with 333 available? I can definitely satisfied. Right, I can definitely satisfy this thing. After that I satisfied this request, then what will happen? It will release the whole resources 110. It will release. Then available will become what? Available will become 333 110, and it will become 3. Okay, it will become 3. Sorry, it will become 4, 4 and 3. Now is 443 is my new available resource. Can I go to the next PJ? Okay, can I go to the next PJ? So that is what is saying, that each PI, the resource that PI can still request can be satisfied by the current available resource plus resources held by the PJ where j is less than equal to I. In that case, with the available resources, can I satisfy the next one? Let me repeat the definition, that system is in safe state if there exists a sequence of all the processes in the system such that for each PI, the resource that PI can still request can be satisfied by the current available resource plus resource held by Pj where j is less than equal to I. So here where j is less than equal to I. So here for my example, I say this is my Pj and this is my Pi. Read in this entire thing in this particular context. So now what will happen, that it will plus current available resource is 333 and resource held by the Pj, that is Pj is this one, is 110. Now I have a 443. I can satisfy this request in sequence. In that sequence, I can satisfy all the requests. Then I'll call it as a safe state. I'll give you much better example after this. That is, if PI needs a resource that not immediately available, PI can wait for PJ to be finished. If P2 required resources and it is not there, but if it is wait for P1 to finish, then definitely more resource will be available, and then it can see whether it can finish it or not. When Pj is finished, Pi can obtain the needed resource, execute and return the allocated resource and terminate. Now when Pi terminates, Pi plus 1 can obtain the needed resource and so on. So this sequence we are calling it as a safe state, and there can be more than one sequence. There can be more than one sequence possible. Okay, so it may not make, I tried here, but if it is not making sense, then we will see next by using this example. If system is in safe state, there is a sequence, then there will be no deadlock occur. And if it is in the unsafe state, then there is a possibility of deadlock. And still it is not saying that there will be a deadlock. Avoidance ensures that system will never enter into a unsafe state. Okay, so this is the purpose of the avoidance. Prevention means we will not allow those conditions to occur that is responsible for the deadlock. But here avoidance means that system will never enter into a unsafe state. So this is the diagram that that satisfy that situation that the deadlock may occur, and here in this case is unsafe state. Then among this unsafe we have a portion that is deadlocked. Safe state, then no deadlock will occur. Okay, now we have a avoidance algorithm. There are two categories, that a single instance of resource type, and in that case we will use resource allocation graph. And we know that previously that if the graph contains cycle, it's a very simple one, graph contains cycle, then in that case we can directly conclude that there is a deadlock. Okay, but if you have multiple instances of the resource type, then we are going to use an algorithm that is called Banker's algorithm, and that will clarify what exactly your safe state is. Okay, so I'll say that if you understand this particular part, this one of Pi and Pj, where j is less than I, then it is totally good. But if you don't, then wait for this another algorithm, and that is called the Banker's algorithm. Okay, so that's all for this. Thank you.